Welcome back. This video is going to talk about the moving average model as well as the ARIMA or autoregressive moving average model. The first order moving average model is defined as follows. My current value of y is going to be some constant plus some random error, but we're going to remember a little bit of the random error that we had before. So this is going to be the random error associated with the previous observation. So this is going to help us handle autocorrelations. We can model autocorrelations in this way. So we're going to be assuming that these theta values are less than 1 so that the process remains stable. If I have theta equal to 0, notice I end up with a white noise process. Now let me issue a couple cautions before we move on. The first caution is that a lot of other textbooks and other software programs flip the sign of theta. So I'm going to be consistent with what's in R. I'm not going to make this a negative as some other books would. But if you're using another textbook, just beware that it might be flipped. Another caution is that this is not at all related to the moving average models that we discussed back in the smoothing chapter. Even though they're called the same things, they're not the same model. Well, let's go look at the backshift representation of this. So why don't we go derive it. So here is my MA1 process. So y sub t is equal to some constant plus epsilon t plus theta times epsilon t minus 1. We can think of this thing, though, as a backshift operator on epsilon sub t. So this is equal to c plus, well, now I can factor out the epsilon t, so 1 minus theta b epsilon sub t. So that is our backshift notation for this. Whenever we've been defining processes in this class, I've given you the mean, variance, and autocorrelation function. Let's do the same for this. So what is the expected value of y? Well, this is really very easy because the mean of epsilon sub t is 0, the mean of epsilon t minus 1 is 0, by assumption here. Therefore, the mean of this moving average process is just c. So that's very easy. The variance is also pretty easy. Let's go write that one out. So what is the variance of yt? Well, that would just be the variance of c plus epsilon t plus theta epsilon t minus 1. Well, the variance of a constant goes away, so we don't have to worry about that. These two errors are independent of one another, so I can just distribute the variance sign across them. I don't need to worry about any covariances. And what I end up with is just the variance of epsilon sub t plus, when this comes out of the variance, the theta gets squared, times the variance of epsilon t minus 1. But this is just sigma squared plus theta squared, and this is also sigma squared since I've got a stationary process. And if we want to clean this up a little bit, we could write it as 1 plus theta squared times sigma squared. So in general, the variance of this process is a little bit larger than the variance of an error. So 1 plus theta squared is obviously bigger than 1, but not terribly bigger. So, if theta has to be less than 1, this thing is never going to be more than twice the size of an error. So that's where that thing comes from. I'm not going to derive the autocorrelation function. I will note, though, that let's plug in some extreme values. So Not that we'd ever have theta equal to 0, but if we did, then the autocorrelation function would be 0. If I put in the largest value that we would ever have, which is something close to 1, I get something close to 1 over 1 plus something close to 1, and I get 1/2. This autocorrelation function between successive observations is never going to be bigger than 1/2. Okay, so that's quite a different story than the moving average. Remember, the moving average autocorrelation function was phi to the k. And so if phi is very large, the autocorrelation could be phi. So 0.99 was a value that we tried in my previous lecture. Another thing to note about this is the autocorrelation function for any observations that are 2 or more away is equal to 0. That's a very important property, and it says if you have an autocorrelation function in ACF where you have a significant value for the first lags and all others are pretty small, that's going to be a signal to you that you probably want to use an MA1 model. That's a reasonable model for that. So remember the rule for the AR process. We use the PACF, and if you only had one significant PACF value, that would signal this could be an autoregressive process of order 1. Well, here we're going to use the ACF. If we only see a single value greater than 1, that's going to be a signal that MA1 is a reasonable model. Whenever we have positive values of theta, we get positive autocorrelations, and these are going to be somewhat smoother than white noise. So as I did with AR1, I've written a little function here to generate data from an MA process. Let's go look at an MA process where my theta is 0.01. So this is very close to white noise. Now, let's look at if I make theta equal to 0.99. So this would be a very large value of theta, indicating we're going to give a lot of weight to both the most recent error as well as the previous error. They almost get the same amount of weight. This appears to be a bit smoother. It's not quite as smooth as the model that we had when phi was 0.99, but still pretty smooth. Let's go look at our ACF. And so remember what I said. The ACF of an MA process should have one significant autocorrelation. And so that is exactly the case here. All my other autocorrelations are pretty close to 0. So that's a hint that you've got an MA1 process on your hands. Well, just as we generalize the autoregressive process, we can generalize the moving average process. Here's a moving average of order Q. In this class, we're going to reserve the letter Q for the order of a moving average process. So Q is always that order. This is that model. So instead of having only the previous error enter into it, we're going to let the previous Q errors enter into our next value of Y. There are additional assumptions in order to get a stable process. I'm not going to go over that with you. We can also use the backshift notation here. So we'll just factor out my epsilon, and then we have this whole term represents the backshift operator applied to the ET, epsilons. The mean and variance of this are quite similar. The theoretical autocorrelation function is going to be equal to 0 for all values of k that are greater than q. So what that means is if we look at an ACF and let's just say the first two values were significant, the first two values of the autocorrelation function were significant, then that would be a signal that an MA2 model would be a good one. We're now going to combine the autoregressive and moving average processes. We're going to call this an ARIMA model, so ARMA. Let's begin with an ARIMA 1-1. So in ARIMA 1.1 says that y sub t is some function of the previous y, so that's the autoregressive part, as well as some function of the previous error. And of course we have the current error. So this is your moving average part, this is your autoregressive part. We can find the backshift notation for this by moving all the y's to one side and keeping all the errors on the other side. So y sub t is some constant plus a coefficient phi times y t minus 1 plus some theta times epsilon t minus 1 plus epsilon t. And so with the backshift notation, we're going to move this term over to the other side. So yt minus phi y t minus 1. But notice this is just b yt. This is equal to c plus, I'm going to change the order of these two, epsilon t plus phi epsilon t minus 1, but this is just b epsilon t. So then this is 1 minus b times my yt value. On the right hand side we have c plus, well, 1 minus b, oops, I forgot my phi here, and I forgot my theta here, times epsilon t. And so that's our backshift note. We can also generalize this. So an ARIMA PQ model would have p lags of y in it, as well as q lags of the epsilons. And we have our corresponding backshift notation. So remember the mean of an AR1 process. So if we had an AR1 process, the mean was c over 1 minus phi, and we derived that in the previous video. If we have an ARP process, instead of just subtracting the first autoregressive coefficient, we have to subtract all p of them. So a couple cautions for us. First off, R doesn't parameterize the ARIMA model as I've written it in the course packet. So instead of using C, R gives you the mean. This is actually more convenient to interpret, as we're going to see in a minute. If you want to know what that constant is, you can always take the formula for the mean and just solve it. This would just be C equal to mu times 1 minus phi1 minus phi2 and so forth. One other word of caution, these models are complicated to estimate. If you use different software packages, you might get slightly different results. Different software packages might use maximum likelihood instead of least squares or vice versa. And so don't get too upset if the numbers don't always match from, say, SAS to R to another package. The general steps that we're going to follow in estimating ARIMA models is we'll pick our P and Q values. We'll go use software. So there is a function in R called ARIMA. You give it the data frame, and then you have to give it the order. So this is the order parameter. You specify P, then you specify 0 for an ARIMA process. So more on what this second argument means in the next video. This is going to be the number of differences. And then you give the moving average parameter Q. Then we can go ahead and compute forecasts. For now, we're just going to use R for that. I'd now like to apply what we just did to the T-bill data that we've been analyzing since, I guess, the first week of class. So these are interest rates. If I use the TS display function that I was recommending in the previous video, we get a time plot. With my domain knowledge that this is an interest rate, I wouldn't be surprised if it's stationary. However, remember with this T-bill data, the interest rates have been basically falling for the past 30 years. They're not going to go below 0. At some point, they're going to go up. But because of this window, it almost looks like there's a negative trend. Let's go look at our ACF and our PACF functions. What we see with our ACF function is that the autocorrelations diminish gradually. When I look at the PACF function, I see one very significant partial autocorrelation. None of the others are significant. This is signaling that I may have an AR1 process. So let's start there. Based on my inspection of these two plots, I'm going to go fit an AR1 process. So the way I specify this is I want a P of 1. We're not going to do any differencing, and I don't want any moving average terms in this model. When I estimate this, what I end up with is the following. So here's my autoregressive coefficient. That's my phi. Then R also gives me the mean. This is not the intercept. So remember, the way I get it back to being a C rather than a mean is I take the mean times 1 minus phi. So I just type that in. And so this would be our intercept. I've stated the model, the estimated model below. So my current value of t is just some constant 0.76 plus 85% of the previous y value, and then whatever the error is. My sigma squared is estimated 2.643. I'm also going to try an ARIMA 1-1 model. The way I specify it is I give the order to be 101. We see now we have an estimate of, this would be our phi, here is our theta, and then this is the mean. I need to convert this mean into an intercept if I want to state the estimated model. So I've done that computation below. And so here is my estimated model. So be sure you're able to state the estimated ARIMA model from the R output. Here is the plot for the AR1 model. And up above, we've got the plot for the ARIMA 1-1 model. And they're quite similar. So a couple things to notice about them is that both of these sets of forecast values are approaching the long-term mean. So what was the long-term mean? In the case of the AR1 model, it was 5.12. In the case of the ARIMA 1-1 model, it was 5.45. And so they're both approaching some value around 5. I also decided to try an exponential smoothing model on this data. So here you'll see I call it ETS. ETS recommends simple exponential smoothing on here. So no trend, of course no seasonality. And when we look at our estimated parameters, the alpha value is 0.999. Basically what we have here is the naive method. The simple exponential smoothing method just says take your most recent value and basically that's going to be your future forecast. We give almost no weight to values prior to the most recent one. What I find interesting about these plots is how much wider the confidence bands are for the smoothing model. So the reason for this is we're putting all of our bet on the most recent observation, and so that's going to give us fairly wide prediction intervals. If we could be having an average of more previous values, so if the previous values were getting more weight in that average, I suspect these confidence bands would tighten up a bit. But in this case, I think we're getting better confidence bands from our autoregressive and our ARIMA model. One more thing about this. If we go back to our AIC values, AIC is saying the ARIMA model is a little bit better. We come to the same conclusion if we use AIC, same conclusion with BIC. They're all basically saying we're better off using the ARIMA model instead of the autoregressive model. I'd like to do one more set of diagnostics on these two models. I'm going to use the check residuals function that we've been using on previous models. Remember, our goal with the residuals is to produce residuals that have no further information in them. They should just appear to be random. If there is a pattern in them, what that signals is there's more things that we can be capturing in our model. So when I look at the time plots for the residuals, they both look fairly random here, although maybe it's drifting downward a little bit, but that it's hard to say. Our ACF for the ARIMA model shows one borderline significant autocorrelation value, signaling that maybe there's a little bit more happening here. When we look at our Young box test, it's borderline significant. The null hypothesis for this is that our ACF values are 0, and so we're not completely sure about that. So when we look at the Young box test for the ARIMA model, the p-value is very large, signaling that we cannot reject the null hypothesis that the first 8 lags are all equal to 0. So I think we prefer the ARIMA 1.1 model for this t-bill data.